Okay, in this tutorial, we're going to ask how we should evaluate the impact of a government policy in the context that we've recently been working with from the perspective of the consumers. So we're going to walk through, set up sort of a framework for thinking about uh, different policy outcomes and walk through how to set up these problems. And at the end, we're going to actually take our model to some data and do some estimation. So that's where we're going. We're going to first set up two um, uh, models for policy analysis. And then we're going to take these models to some data. So this is, I think, going to be a pretty fun tutorial. This isn't going to be on the mini exam or the homework. This is sort of an extension of what we've just been talking about with the consumer's problem. Uh, so when we think about government policies, you're probably familiar from your intro economics class, sort of the range of policies we typically think about in most economics classes at this level and below. Uh, we tend to look at like trade policies. This can be, you know, uh, things like tariffs. I can't spell, but I think that's correct. We can look at subsidies, quotas, and what we're going to do in this video is actually look at a gas tax, which is one of my favorites. Okay. So when we think about policies, the main way we evaluate whether a policy is good or not is based on whether its benefits exceed its costs. Do its benefits uh, outweigh its costs? This is a generally pretty loose concept. So one way we can make this idea a little more formal is to write down an equation like this. So we're going to look at everyone in the world. We're going to call each person I. We're going to sum over all of their benefits. And benefits for subscript I just denotes the benefits of person I. And we just want to make sure that the benefits exceed the costs. So this is slightly more formal. The way we measure benefits and costs is going to be important. But this is sort of our first uh, pass at defining how we consider uh, the impact of a government policy. So we're going to set up a model. So the motivating example here is a gas tax. So we're going to impose a gas tax. And we're going to leave the gas tax general for a moment. And in addition to the gas tax, we're going to look at one individual with a Cobb-Douglas utility function. So you're all familiar with this at this point. We have u of two arguments, and the two goods we're going to look at in this model. On the vertical, we're going to have F standing for food, and on the horizontal, we're going to have G standing for gas. So utility is going to take F and G, and it's going to look really familiar. We just have F to the alpha, G to the 1 minus alpha. And we can rearrange the utility function, or excuse me, the budget constraint. We have the price for F times F plus the price for G times G. And this is pre-tax. Post-tax, we actually can write our budget equation in the following way. So we're placing the tax on the buyer. And we're placing it on the gas. And we're going to say for each unit of gasoline, there's going to be 1 tau's worth of tax imposed. So we're just raising the price by tau. Okay, so let's just set this up visually, and we'll come back to this problem. So we have y over pf. We have y over pg. And we have our indifference curve, which gives us our optimal bundle. Okay. And let's just call these F1 and G1. Okay, so at this point we have our consumer's problem as a model, and we have this concept of a tax. But we want to take our notion of costs here and map our model of consumer behavior onto the idea of costs. For this video, we're actually going to abstract away from the idea of the benefit side of this equation. This comes into play when we talk about externalities. And if any of you have taken a environmental economics course or plan on doing it, this is really the point of that class, is looking at the benefits of policies that mitigate externalities. But here we're just going to look at the cost side. So the question next is, how should we evaluate, how should we measure costs in this environment? So we're going to set up 2 different methods. And there are more than two. We're just going to look at these two because they're most closely related to our consumers problem, which we're most familiar with at this point. This policy. Okay, so the first one is what we call compensating variation. And I can't talk and write at the same time. Or spell. What am I good for? It's a good question. Is the amount of additional money we need to give a consumer to make them just as well off as before the policy. Okay. So essentially we're just saying how much do we need to give the consumer to make them sort of live on the same indifference curve. That's the intuition you should maybe be thinking in the back of your mind. And if this is reminding you of the Hicksian, that's fantastic. So the way we can write compensating variation is just the difference between the expenditure after the tax in this case. So we have the price for F, the price for G, plus tau. So this is the post-tax price for gasoline. And then we have our U bar, which is this indifference curve. So all we're saying here is let's just make sure we're still on the original indifference curve with our new prices. And that's the expenditure. And then we just subtract off the original expenditure. And in the tutorial videos, in tutorial 4, I actually included this on one of the graphs, this compensating variation. So to set this up visually, we'll just extend our consumer's problem. So we have our original budget constraint. We have our new budget constraint. So our x-intercept originally was y over pg, and now it's y over pg plus tau. Which means with this new budget, we end up on a lower indifference curve. And we know from the Cobb-Douglas, the non-taxed quantity will stay the same. Okay, but compensating variation does something that looks like what the Hicksian is doing, where instead of holding income constant, we're holding utility constant, which means we just want a parallel shift. We want to shift this way in the budget constraint until it hits this point. So this is our new indifference curve. Excuse me, our new budget with the expenditure defined here. So our compensating variation is just this difference here. It's defined by this difference. Okay. Another way of looking at this is to set up the Hicksian demand relationship. So we, instead of looking at both G and F, we can actually set this up with price on the vertical and quantity on the horizontal. So we have price on the vertical and quantity of G on the horizontal. And our Hicksian demand gives us some relationship like this. So this will look pretty similar to what you've encountered with consumer surplus, where we look at the price before. So price before is PG, and then the price after, which is PG plus tau. And then we just find the area between these two prices. And this is, in this case, this is the compensating variation. And if your notion of consumer surplus is playing prominently in your head at this moment, that's great. We're going there next. But to find the area under this curve, or to the left of this curve, we first need to realize, if you remember, that Hicksian as a function of the price is equal to the derivative of the expenditure with respect to the price. So our change in expenditure, which is our compensating variation, is equal to the integral from PG to PG plus tau over the Hicksian. So we're just integrating between P and PG over this interval. Okay. You can think of this as integrating under the curve, if you'd like. You can flip the axes, and this just becomes finding the area under the curve. But we're just doing it to the left of the curve. Okay. So the second method for evaluating policies is consumer surplus. This is probably the one you're more familiar with, but let's define it anyway. Consumer surplus is the difference between the maximum amount a consumer is willing to pay, and what the good actually costs. At the chosen quantity. Okay. So this is the definition for consumer surplus. What we're after is the difference in consumer surplus. So we're going to say delta CS is equal to the consumer surplus with the tax minus the consumer surplus without the tax. And this is what we're after. So let's set this up in the way that looks familiar. So on the vertical, we have price. On the horizontal, we have quantity, which is what we've been calling G. And we have our demand curve, which looks like this. And we have two prices, price before, which is PG, and the price after, which is PG plus tau. So our consumer surplus is, again, going to be the area to the left of this curve. The change in consumer surplus is the area to the left of this curve. And this looks really familiar, or really similar to what we did with compensating variation, except instead of using the Hicksian, which is accounting for the changes in expenditure, here we're just looking at the change in consumer surplus, which is the difference between what's paid and what would have been paid. Okay. And we can write out what consumer surplus, how we would calculate it. The change in consumer surplus is just, again, an integral from PG to PG plus tau. But here we're just integrating over D. Okay. And just to note here, if we were to draw the Hicksian on this same graph, it might look like this. And this area here, let's call this, this is just the difference between the compensating variation and the change in consumer surplus. So just visually, it should be clear that most of the time when the Hicksian and the demand curve don't align, that the change in consumer surplus and the compensating variation should not be equal. And in general, the compensating variation is going to be slightly larger than the change in consumer surplus. And this is really just coming from the income effect. When the Hicksian lies closer to the vertical axis than the Marshallian demand, this inequality is reversed, which typically happens with inferior goods. As you would sort of expect, the income effect isn't going to dominate the substitution effect. Okay, so let's go ahead and do a little bit of math. This is not something I'm going to ask you to do on your own, but I just want to show you how it can be done. I think a lot of times just seeing what's available can guide your own curiosities. So first we're going to set up the Hicksian and the Marshallian demands. So we've already gone through and actually calculated the Hicksian and the Marshallian for the Cobb-Douglas. So our Hicksian is just U bar times PF over PG, 1 minus alpha over alpha times raised to the power of alpha. And our Marshallian is 1 minus alpha times y over PB. Wait, PG. Okay. So first we're going to go ahead and use the Hicksian demand to calculate compensating variation for the stacks. So again, compensating variation is just the integral from PG to PG plus tau over the Hicksian. So in this case, we'll just substitute in our Hicksian. And instead of writing PG here, because we're integrating over PG, but it's all, PG is also in our integral, then we should write X just to make our notation clear, or some other variable. And then we just integrate over that running variable. Okay. So I'm not going to write out all the steps here, but we'll just bring everything that doesn't depend on X to the outside, which gives us U bar 1 minus alpha times PF over alpha raised to the power of alpha, integral from PG to PG plus tau, and this is 1 over x to the alpha dx. And here, this thing just becomes one over x to the alpha times 1 over alpha minus 1 and we have alpha minus 1 PG plus tau. So now we're evaluating at the upper and lower. So let's just write this all out in one final step. And again, this is not something I'll ask you to do. So here we have 1 over PG plus tau raised to the alpha minus 1 minus 1 over PG raised to the alpha minus 1. And I'm also going to bring out the 1 over alpha minus 1. So we'll multiply that alpha minus 1. Okay. And then we can do simplification here if we'd like. But this is how messy these types of integrals often end up looking. But it gives us a closed form, and we can take any values that we end up estimating and use this functional form to estimate the policy impacts. So second, we're going to calculate consumer surplus using the Marshallian demand. So the change in consumer surplus is again an integral over 1 minus alpha times y, and then we have 1 over pg, but because we're integrating over pg, we'll use x as our running variable. So then we have pg plus tau and pg. And long story short, this just comes out to be 1 minus alpha y times ln pg plus tau minus ln pg. Okay. So this is maybe a little cleaner, but it's still not so fun. But this is sort of a peek behind the curtain. We often do this type of math where we run integrals over demand equations to calculate values that we care about. So to close out, what we're going to do next is actually take our model to some data. So I've collected some data from a gas tax study. So what we're going to do, I'm just going to write down some point estimates from this study. Okay, so our elasticity, income elasticity of demand is 0.66. Our price elasticity of demand is negative 0.56. We have an average quantity demanded of 392 gallons in 2013. We have an average price of $3.50 in 2013, and we have an average income of 52,000 again in 2013. Okay, so the next step I'm going to take is to deviate slightly from the demand curve we walked through above. And this just makes our life a little simpler when we're dealing with data. What we're going to assume is that elasticity is constant. And if this is true, then our demand curve looks like the following. QD equal to beta, which is just some parameter, times price raised to the power of price elasticity of demand, times income, which is raised to income elasticity of demand. You'll notice this looks somewhat similar to our Cobb-Douglas, where we have price raised to some power times income raised to some power, and then we have some coefficient out front. But here, the main difference here is that y has some power. We're not going to get into the details of where this comes from in this video. So just take it as given. So here we have, we're going to substitute in our numbers. So we have beta times price, and then we're going to raise it to elasticity of demand. So this gives us negative 0.56. And then we have y, which is raised to the power of 0.66. Okay, so this is great, but we don't quite have enough information because we still have beta. It's a parameter and we don't know what the value is just yet. So what we're going to do next is calibrate using the means. Using the means. So we have more information here about averages. So what we're going to do is plug in these three averages into this demand equation we've solved, or we've constructed, and solve for beta. So to write this out, all we have to do is rearrange our demand equation to isolate beta. So we have P raised to its power, Y raised to its power over QD. And then we're just going to plug in our average values that we've been given. So this looks like 350 raised to the power of 0.56 times our average income raised to the power of 0.66 over our average quantity demanded yearly. And if we plug this into a calculator, this comes out to be just about 0.626. So that means our demand equation is QD 0.626 times price raised to the 0.56 times income raised to the power of 0.66. Okay, so we're simplifying our model using this simplified model with the data we're given. Then what we can do with this is calculate the change in consumer surplus. And we're not going to use compensating variation in this example. We're primarily working with the demand curve. So the appropriate measure with the demand curve is the change in consumer surplus. So we're going to walk through this example, and we're going to look at what happens to the change in consumer surplus with this this tax. And we're going to use we're going to use a $1 tax. So before, the price was $3.50. Now the price goes up by $1. And then we're just going to use our demand equation and integrate over price. So we have 0.626 times price raised to the 0.56 times y raised to 0.66, and then integrate over price. And here I'm using p because we don't have p in the limits of the integral. Okay. So when we run through this integral, that's going to give us, I'm just going to write it out here, 0.626 times y, 0.66. And then we have price raised to 0.42, and then we evaluate that at 3.5 and 4.5. And at this point, plugging this into a calculator should give us 0.281 times y, 0.66. Okay. So just looking at a range of incomes, the first thing we can do is look at what happens. So let's plot change in consumer surplus on the vertical axis and y on horizontal axis. So we want to see what happens when we change prices. Excuse me, when we change incomes. So we're asking the question, how does this tax policy affect different people at different income levels differently? And so generally, so if the exponent here was 1, we would see an upward slope that was linear, and the slope would be determined by this coefficient here. But what we're actually seeing is something that looks more like this. So this is our change in consumer surplus. So this shows us that as income increases, the change in consumer surplus as a result of the tax is actually going up. But what we can also do is look at what happens to the change in consumer surplus divided by y. And the reason we might care about this measure instead of consumer surplus is that the larger your income, the larger your loss, and the more original consumer surplus you might have. So even if the loss in consumer surplus for small incomes is smaller than it is for large incomes, we might actually be worried that we're impacting smaller income households uh, relatively more. So to do this, let's just construct our measure here. So we'll just take our changing consumer surplus and divide it by y. So that's going to give us y, and we're just going to subtract off 1 from our exponent. So we have negative 0.44. And here we get the opposite direction. So the shape generally looks like this. So it's not linear, and it's decreasing. So this tells the opposite story, that as a percentage of income, this tax is regressive. Okay, so that's sort of the scope of what we're doing with policy analysis here. There are a few other things we could do, but we're going to leave it here for this tutorial. Take a look at the textbook. It's a really good chapter to read through. There's a lot of important information in the chapter that I'm not able to get to in this tutorial. So take a look there. And I will see you in the next one.